The International Space Station has always been a symbol of global-scale logistics, entirely dependent on a constant chain of resupply missions from Earth. But inside Tiangong, a different reality is taking shape. With its advanced life support systems, onboard 3D printing, and experiments in regenerative ecosystems, Tiangong is rapidly moving from a dependent outpost to a self-sufficient habitat. This transformation is quietly solving the single biggest obstacle to deep space exploration, turning science fiction into operational reality. Strap in. For over 2 decades, human survival in space has depended on Earth's umbilical cord. The International Space Station requires 2.5 tons of supplies every month, including food, water, spare parts, and scientific equipment. Every meal, every breath of oxygen, every replacement component travels 400 kilometers from the surface. This model worked for scientific research, but it revealed a fundamental limitation. Humans could visit space, but could not truly live there independently. China studied this dependency carefully. When they began planning Tiangong in 2010, they designed around a different philosophy: gradual self-reliance. Not just as a cost-saving measure, but as the foundation for humanity's expansion beyond low Earth orbit. The stark reality is that missions to Mars or permanent lunar settlements cannot function with Earth as their lifeline. The math simply does not work. A Mars mission would require prohibitive amounts of supplies, and the distance makes emergency resupply impossible. This is not just a technical challenge, it is an existential one for our species becoming multiplanetary. Tiangong's development came after careful study of both the successes and limitations of previous space stations. While the ISS demonstrated incredible international collaboration, its dependency model could not scale to deep space. The Chinese space program recognized this fundamental barrier and made a strategic decision to prioritize technologies that would eventually enable full self-sufficiency. Traditional space stations recycle about 75% of their water and 50% of their oxygen. Tiangong's environmental control systems push those numbers to 95% and 85% respectively. The station's regenerative life support doesn't just filter air and water, it actively produces them. Advanced electrolysis systems split water molecules with precision. Atmospheric processes scrub carbon dioxide and convert it back to breathable oxygen. What's truly revolutionary is that China recently announced its Tiangong life support system has achieved 100% oxygen regeneration. This milestone was confirmed by Bian Qiang, Director of the Environmental Control and Life Support Engineering Office at the Astronaut Center of China. Even human waste becomes a resource, processed through bacterial digesters that create fertilizer for experimental crops. This closed-loop system reduces the need for Earth resupply by approximately 6 tons every year, a dramatic efficiency improvement that transforms the economics of long-duration spaceflight. In 2025, the Shenzhou 19 crew conducted groundbreaking experiments in artificial photosynthesis using semiconductor catalysts in a simple draw-style device to convert carbon dioxide and water into oxygen and ethylene, a hydrocarbon that can be used as rocket fuel. This technology operates at room temperature and normal pressure, consuming far less energy than traditional methods. Unlike the energy-intensive electrolysis used on the ISS, which consumes up to a third of the station's power, this revolutionary approach mimics nature's own processes to create not just life-sustaining oxygen, but also the components needed for propulsion. Perhaps most revolutionary is Tiangong's onboard manufacturing capability. While the ISS relies on Earth for replacement parts, Tiangong carries advanced 3D printing systems capable of producing everything from tools to electronic components. This is not just about convenience, it is about survival on missions where Earth resupply is measured in months or years, not days. When a critical part fails during a Mars mission, waiting for the next supply ship is not an option. The ability to manufacture replacement components on demand is the difference between mission success and catastrophic failure. The station is equipped with specialized 3D printers that can work with various materials, including metals and polymers, to create both simple tools and complex components. Chinese engineers have been testing the production of increasingly sophisticated parts, gradually building a library of printable components that could support extended missions beyond Earth orbit. The bioprinting experiments go even further, testing the production of medicine and potentially human tissue in microgravity. This capability transforms how we think about medical care during long-duration missions, reducing dependency on pre-packaged pharmaceuticals with limited shelf lives. The station's agricultural modules represent the next step towards self-sufficiency. Hydroponic systems grow fresh vegetables in controlled environments. LED arrays provide precise light spectrums for optimal plant growth. Even the waste heat from electronics is recycled to maintain growing temperatures. Current experiments focus on lettuce, radishes, and herbs, but the ultimate goal is protein production through aquaculture and cellular agriculture. The math is simple. A mission to Mars cannot carry 3 years of food. Since the Tiangong 2 Space Lab missions, scientists aboard Tiangong have been conducting experiments growing lettuce in space. These studies help understand how plants respond to microgravity conditions and optimize growing methods for future deep space missions. By combining hydroponics with the station's water recycling systems, Tiangong creates a partially closed ecological loop, each system supporting and enhancing the others. Food scraps become compost for new plants. Plant transpiration contributes to water purification. The plants themselves help manage carbon dioxide levels while providing psychological benefits to the crew. What does self-sufficiency feel like for the taikonauts living inside this system? Their morning routine begins with checking the station's autonomous systems, not because they need constant human intervention, but because understanding your environment is crucial for true independence. Breakfast might include vegetables harvested from the growth modules just hours earlier. The water they drink was recycled from yesterday's waste. The oxygen they breathed was generated overnight by the station's own systems. This is not just efficiency, it is a psychological shift from visitor to resident. The crew's relationship with their habitat becomes more intimate and cooperative. They are not merely occupants, they are active participants in a complex ecosystem where human activity and technological systems are deeply intertwined. This integration changes how the taikonauts think about their role in space. Traditional astronauts describe a constant awareness of Earth's support, every supply mission a lifeline. Tiangong's crew reports something different, a sense of actually living in space rather than surviving in it. Private sleeping quarters provide genuine privacy. The ability to prepare fresh meals creates comfort routines. Most importantly, the knowledge that their station can sustain them independently reduces the psychological pressure of complete Earth dependency. This mindset shift is perhaps the most profound change occurring aboard Tiangong. The sense of agency that comes from self-sufficiency has deep psychological benefits, creating a more sustainable emotional state for long-duration missions. When taikonauts know they can manufacture replacement parts, grow their own food, and regenerate their own air and water, the isolation of space becomes less threatening. This psychological resilience will be essential for missions to Mars and beyond, where communication delays and the impossibility of rapid return to Earth create unprecedented psychological challenges. With basic survival automated, the crew's focus shifts from maintenance to advancement. Daily schedules emphasize scientific research, system improvements, and habitat expansion testing, the work of building rather than merely maintaining. This shift is profound. They are not just operating a machine, they are developing a home. The station becomes a living laboratory where the boundaries between work and living space blur. Experiments are not just abstract scientific pursuits, they are investments in the crew's future independence. Taikonauts' daily activities increasingly focus on improving and expanding their capabilities, rather than just maintaining existing systems. They spend time testing new manufacturing techniques, optimizing plant growth, and enhancing recycling efficiency, each improvement bringing them closer to the goal of complete self-sufficiency. Every system aboard Tiangong serves a dual purpose, supporting current operations and testing technologies for deep space missions. The closed-loop life support isn't just efficient, it's practice for Mars, where resupply is impossible. The onboard manufacturing capability rehearses for asteroid missions where spare parts must be created from raw materials. The agricultural systems prototype the food production required for multi-year interplanetary journeys. China isn't just building a space station, they are systematically removing the barriers to a permanent human presence beyond Earth orbit. Each experiment, each improvement in recycling efficiency, and each new manufacturing capability is evaluated not just for its immediate utility, but for its application to future missions. The recent breakthrough in artificial photosynthesis is particularly significant because it demonstrates the ability to generate not just life support essentials, but also fuel components from waste products. This capability could enable missions to refuel in deep space, dramatically expanding the potential range of human exploration. China's long-term vision extends far beyond a single space station. Tiangong serves as the prototype for modular, self-sustaining habitats that can be replicated and scaled. Future plans include permanently crewed lunar stations using Tiangong's life support technology, asteroid mining operations, supported by onboard manufacturing, and eventually the first self-sufficient Mars colonies. Each step builds on lessons learned from this orbital laboratory. In October 2023, China announced revised plans to expand the station to 6 modules starting in 2027. This expansion will provide additional space for advanced self-sufficiency experiments and larger-scale manufacturing facilities. The Chinese space program is also developing inflatable and reconfigurable modules for on-orbit manufacturing, recently completing ground tests of what they describe as a reconfigurable, flexible on-orbit manufacturing platform. This technology could enable large-scale production facilities that bypass the size limitations of traditional rocket fairings. The real breakthrough isn't the technology, it's the mindset. Tiangong proves that humans can create closed-loop ecosystems beyond Earth. Every recycled breath, every harvested vegetable, every manufactured tool represents a step toward genuine space independence. The station's legacy won't be measured in years of operation, but in the permanent human settlements it makes possible. We're witnessing the transition from space exploration to space habitation. What's happening aboard Tiangong isn't just about Chinese national achievement. It represents a fundamental shift in humanity's relationship with space. By systematically solving the challenges of self-sufficiency, China is creating the foundation for a multi-planetary future. These advances don't just benefit a single nation, they expand the frontier of what's possible for our entire species. The technologies being perfected aboard Tiangong today will likely become standard features of all future deep space habitats, regardless of which nations or organizations build them. This self-contained ecosystem, floating 400 kilometers above Earth, represents more than technological achievements. It represents evolution. The difference between visiting space and living there, between dependence and independence, between exploration and expansion. As Tiangong continues to perfect these systems, it's not just advancing Chinese capabilities, it's solving fundamental challenges that every spacefaring civilization must overcome. The principles being tested in these modules will enable permanent human presence on the Moon, on Mars, and eventually throughout the solar system. What we're witnessing inside Tiangong isn't just the future of space stations, it's the blueprint for humanity becoming a truly multi-planetary species. Each recycling system, manufacturing capability, and food production experiment brings us one step closer to breaking free of Earth's gravitational and logistical constraints. The implications extend far beyond space. The closed-loop sustainability systems developed for Tiangong have direct applications to Earth's growing environmental challenges. Technologies that can recycle air, water, and materials with near-perfect efficiency in the harsh environment of space can revolutionize how we manage resources on our home planet. The age of space survival is ending. The age of space living has begun. What began as an engineering challenge is transforming into a new chapter of human civilization, one where our species exists not just on Earth, but among the stars. Space Envisions brings you the cutting edge of space exploration and technology. To learn more about how today's innovations are shaping tomorrow's reality, subscribe and join us as we envision humanity's future among the stars.